Okay, so here's our notes on types of radioactive decay. So you should have your note sheet that was on Classroom to go ahead and fill in your notes. All right, here we go. All right, so the first type of radiation decay we're going to talk about is called alpha. And as you can see, this is the picture for alpha. There are 2 protons, 1, 2, because protons are positive, and 2 neutrons. So when we're talking about decay, we're really talking about the nucleus and what's happening in the atom's nucleus. So we're really talking about protons and neutrons, okay? And so the Greek letter that we use to represent this is alpha, so it looks like a little fancy A. The representative picture is here. It's 2 protons and 2 neutrons. The symbol that we do is for helium, helium-4, the isotope helium-4. And why do we use that? Well, because it has an atomic number 2 because it has 2 protons. And it has a mass of 4 because it has 2 protons and 2 neutrons. Now, it doesn't have any electrons. We don't really talk about the electrons. So we're really writing our isotope symbol when we're talking about this, just about the nucleus itself. Okay? All right. So what about the definition? So alpha radiation is a positively charged, because there's no electrons, so we have 2 positives and 2 positive protons, and neutrons are neutral, charged particle that consists of 2 protons, 2 neutrons bound together. It is released by an atomic nucleus undergoing radioactive decay and is identical to the nucleus of a helium atom. That's why we put the symbol He for helium. Because of their relatively large mass, alpha particles are the least powerful and least penetrating forms of nuclear radiation. So what does that mean? So remember probably back in atomic history, and we talked about the gold foil experiment with Thomson, and I said that he was releasing positive particles. These are the particles he was actually releasing, were alpha particles. And it was a part of a decay. So he was releasing these, and that's how he discovered the dense positive nucleus, is through alpha particles. All right, so how does alpha radiation change an atom? Okay, first of all, it decreases the atomic number by 2. Remember, we said it's being released, which means it's being removed from the actual nucleus. So it is decreasing the atomic number of the element that's decaying by 2, because we're releasing 2 protons. So it's going to change what the element is. And then it decreases the mass by 4, because we're releasing 2 protons and 2 neutrons. The mass of whatever we're decaying is also to increase by 4. So here's an example of chemical reaction. So if we start with radon, 226, radon has an atomic number of 88. Nothing happens, so it's not fission or fusion. Remember, it's just decaying. It's breaking down. Decay means breaking down. So it's going to release 2 protons and 2 neutrons, which we're going to write the nuclear nuclear notation, sorry, my brain's not working, as this way, with a mass of 4 and an atomic number 2 of helium. So notice from 226, we're going to subtract out 4 to get a total mass of 222. So that mass decreased by 4. And then from 88, we're going to subtract out 2 protons. Those are going to leave. So 88 minus 2 gives me 86. And now we have an element atomic number Rn. So it'll decay, radon will decay into Rn and a helium type of particle, or an alpha particle. Okay, this is not actually a helium atom. I know it's a little strange because there's no electrons, but it is an alpha particle. All right, the second one we're going to talk about is beta radiation decay. And so in beta radiation decay, we are actually losing electrons. And there's a couple different things that can happen in beta decay to lose that electron. But the first thing is the Greek letter we write as B. This is beta, the Greek letter beta. The representative picture is this here as an electron. And we write it, the symbol, this way. So electron is E. Remember, it has a mass of 0 because electrons are not included in our mass. And it has no protons, but instead of a 0, we put the charge. Remember I talked about in fission and fusion that actually it's not just the atomic number, it's the charge. So you noticed in that helium atom, it had a charge of 2 protons. An electron has a charge of -1. All right, so let's talk about a beta decay definition. So what is it? Well, it is a high-speed electron, or sometimes we call it a positron, which is a positive electron. Why is it a positive electron? We don't know it. We just know it exists. And then usually emitted by an atomic nucleus undergoing radioactive decay is a beta particle. So again, it's a decay, so we're breaking down the nucleus. We're breaking down the atom, making something new. Beta radiation occurs when a neutron, and this is strange, a neutron, so we're losing a neutron, decays into a proton. So we'll add to the, so it's a neutron that actually decays into a proton, and then it emits an electron. So it kicks out an electron. And then beta radiation also occurs when a proton, so it's the second way beta radiation happens, proton decays into a neutron and emits what we call a positron. Very strange. Beta particles have greater speed and penetrating power than alpha particles, and can be stopped by a sheet of aluminum. So these are our second strongest. So our weakest decay is alpha, and then it's beta. So let's look at it. So how does it change an atom? Well, it increases the atomic number, and it by 1. I forgot to put that in there, so I'm going to put that in there right now. It changes it by 1. Okay, so let's go take a look. Let's see if it changes it there for me. By 1. Okay. Changes it by 1. There we go. And so therefore it changes the element. And then does not change the mass because electrons don't have any mass. So here's an example. So we have lithium, and this one's a little bit confusing. It does take some practice. So take a minute, think about it. So we have lithium, which has a mass of 8 and atomic number of 3. We're going to remove, and we always write it as an electron. Even though it may be a positron, neutron, we always kick it. When it kicks out, we just write it as an electron. Okay? We don't worry about putting a positive one on it. So if it's going to remove it, that means we're subtracting out. So 8 minus 0, so the mass of 8 minus a mass of 0 still gives me a mass of 8. Now, this is where the confusing math thing, and you have to remember your math rules, is we're going to do 3 minus a negative 1. So when we minus that negative 1, it's plus a positive 1, so then we get an atomic number of 4. And then the atomic number 4 would be beryllium. And we're going to practice this on our worksheet. Okay. All right, the last one we're going to talk about is gamma radiation decay. So the Greek letter looks like this. This is the Greek letter gamma. The representative picture, it has no particle coming out. It actually is what we call a gamma ray. But how do we write it in the equation? We write it this way. So it has a mass of 0, has a charge of 0, and it is a gamma. So we write it this way in an equation. Okay. All right. All right, what's the definition of gamma radiation? It is a stream of high energy electromagnetic radiation given off by atomic nucleus undergoing radioactive decay. Not a particle, just energy. Greatest speed and power of these 3 types of radioactive decay. This is the stuff that causes radiation poisoning, is when we have a gamma radiation decay. Okay? And so how does gamma radiation change an atom? It does not change the atomic number or mass. Remember, it's 0, 0. It does not change the element. Here's an example. So a lot of times too, you'll see here, and we won't really worry too much about it, but I just kind of want to introduce it to you guys. There will also be a beta emission before it goes to the gamma, but that's okay. All right, so if we start with cobalt, Usually this is how it goes, but really we're going to more focus on this one. This one says it does start with cobalt, gets turned into nickel because it goes through beta. But we're going to start here, okay? So notice nickel, 60, mass of 60, and atomic number 28 is nickel. It's going to release a gamma photon, which is, remember, photon is just another word for light or a gamma ray. And notice it doesn't change it, okay? It goes from nickel to nickel, okay? And so that's the one thing that is coming off. What happens is it's just really excited. And so that excited energy that has to go away, it can't keep it. So to become more stable, it just kind of gets rid of that energy or that gamma ray, okay? All right. And remember, I always remember, gamma radiation is what created the hole. Okay. All right, so this is kind of an overall kind of picture, and this is the top of your notes, is we have the alpha particle here with our 2 protons and 2 neutrons. So color that in whatever 2 colors you want. Note you're going to make a key there too, which ones are protons, which ones are neutrons. And alpha particles actually can be blocked by paper. And so that's why Thomson used these because they didn't cause any damage. And he could actually just put paper around there and it would block those alpha particles from even reaching him. Beta is aluminum. It's blocked by aluminum. So beta particles can go through paper, but once they hit aluminum, they actually bounce back. And this is why gamma radiation is the worst. So gamma radiation goes through paper, goes through aluminum, and is blocked by lead. And yes, as we talked before, X-rays, we use lead vests to block the X-rays. They can give off a type of gamma radiation, but not as bad as what you would have seen in Chernobyl, because remember, this is just a photon. Those neutrons is what really causes the problem. And so gamma radiation does cause some cell damage and DNA damage, but it can be blocked by lead. Okay? All right. Here's a couple learning checks. Let's see how well you learn these, okay? All right, true or false? Alpha particles consist of 2 protons and 2 neutrons. So, really quick think about, is it true or false? Okay. And then, which of the following does not change the nucleus of an atom? Alpha radiation, beta radiation, gamma radiation, or all of the above. So, really quick, write those on your thing, and then I'm going to go over those answers. Okay? All right, so let's go back to the first one. Alpha particles consist of 2 protons and 2 neutrons. This is true. Remember, an alpha particle, it's just 2 protons and 2 neutrons are released for a total mass of 4 and an atomic number of 2. Second question, which of the following does not change the nucleus of an atom? That would be gamma radiation. So gamma radiation leaves the atom nucleus intact. It just releases the gamma photon. All right. Hopefully you are in class or got to make it, because then you get to play nuclear war. If you have any questions, let me know.